whenever you see it goes to infinity, there's only one you can actually solve for. So if it's arithmetic, you can't solve it at all. If it's geometric, what you're doing is you're checking to make sure it is convergent, which means it's going to 0, which means your R value has to be less than 1, or the absolute value has to be less than 1. So, like I said, you're going to note first that it's geometric. It's geometric because it's exponential. It is infinite. So it's geometric, infinite, you have to check your R value. You have to make sure your R value, absolute value, is less than 1. Can someone tell me what the R value is on this one? What is my common ratio on this problem, Rena? It is 1/2. Your R value is always the base of your exponent. This is your R value. So when it's geometric and infinite, the first thing you're going to do is make sure your R absolute value is less than 1. So in this case, we're going to have is 1/2 absolute value less than 1. Yes, it is. So you can actually find the sum. As soon as you know you can find the sum of a geometric, you have a formula to solve this. Your formula for an infinite geometric convergent sequence is going to be your sum equals your first term divided by 1 minus R. R is 1/2. That isn't the hard one in this one. The hard part is you actually don't have an a sub 1 as being your first term. Your first term is actually plugging a -1 in. So this right here is when I plug a -1 in. Your first term is when you plug a -1 in. So in order to get this going on, the first thing you need to do is actually find a sub -1 as your first term. So that means we're plugging a -1 in for that n. So we're going to have 3 times 1/2 to the -1 minus 1. Well, that's going to equal 3 to the 1/2 to the -2. When you have a negative exponent, all that's telling you to do is flip the fraction and then treat it like a positive exponent. So 1/2 to the -2 is actually 2/1 squared. This would equal 3 to the 2/1 squared. That would be 3 times 4, which equals 12. So your first term is actually 12. So the sum is going to equal 12 divided by 1 minus your R value, which is 1/2. That is 12 over actually 1/2, which is 12 times 2, which is going to equal 24. Your correct answer should have been D, 24. If you ever have a multiple choice problem with these, a good thing to do is just plug in your -1, plug in maybe 0, plug in 1, and you're going to be able to see what number you're getting close to. You'd realize that this is not in the realm of possibilities. It's not going to get this big. It's going to go to 0 really, really quick. All right, questions on this one? Okay, then we'll quickly go over questions from the homework. Hope. Number 43. Number 43 says, choosing a prize, a committee has 4 different VCRs, 3 different CD players, and 6 different CDs available. The person chosen as outstanding freshman will receive 1 item from each category. How many different prizes are possible? So we have 4 different VCRs, we have 3 different CD players, and we have 6 different CDs available. Whoever wins get to pick 1 from each of those group. Well, that sounds like our fundamental counting theorem. It's the one where you are choosing 1 pair of pants and 1 shirt. It's almost like you win 1 pair of pants, you win 1 shirt. We're just replacing shirts and pants with VCRs, not TVs, is it? VCRs, CD players, and CDs. This must be really relevant. So if we have 4 VCRs to choose from, we're going to pick 1 of the VCRs. Then we're going to choose 1 of the players, and we're going to choose one of the CDs. So fundamental counting theorem says if you're pulling one from each group, you just multiply your total possibilities together, and you would just have 4 times 3 times 6 equals 72. Not quite a permutation one. Permutation is always when we're decreasing by 1, where we are choosing 4 of one big thing like the players. All right, other questions? Yeah. 47 says, phone number. How many different 7-digit phone numbers are available in Jamestown if the first 3 are either 345, 286, or 329? And the last 4 can be any ones, right? It could be 1111, 00000. So let's just tackle those last 4 digits. Those last 4 digits, 1, 2, 3, 4. I have 10 possible for the first of the 4. I have 10 possible for the next one. I have 10 possible for the next one. I have 10 possible for the next one. Does that make sense for the last 4? Because I'm just picking one from each group, which would be our fundamental counting theorem, so I can multiply it together and I get those choices. Well, we only have 3 possible kind of first 3 of our local, right? They said it has to be either 329, 345, and 286. So that means your first ones only have 3 possible you can choose from. You're not going to choose each individual one. There's only 3 possible ones. There's only 3 branches. So either you have a 329, and then you branch off into these. You have a 345 branches off to these, or you have the other one and it branches off to there. So it's really just 3 times 10 times 10 times 10 times 10. Other questions? Questions going once? Going twice? All right, back to the results. If I choose a president, a vice president, and the secretary, you care what position you get. Which position you're in changes the outcome of the thing. So we're going to talk about what's the difference between combination and permutation. In English, we use the word combination loosely, without thinking if the order of things is important. In other words, the first thing says, my fruit salad is a combination of apples, grapes, and bananas. We don't care what order the fruits are in. They could be bananas, grapes, and apples, or grapes, apples, and bananas. It's still the same fruit salad. Order does not matter. Whatever you put in, you're going to end up with the exact same result. On the flip side, think about the combination to a safe. Your combination to your safe is 472. If you go to your locker and you do your numbers out of order, does your locker open? I hope not. Your locker, you have to type in, or you have to do 472 in that particular order. Order definitely changes the result of your locker combination. So in mathematics, we use more precise language. When the order doesn't matter, we use something called combination. So if we look at that fruit salad one, this is considered a combination problem. I don't care whether you added my grapes first, or my apples first, or my bananas first. It's still the same fruit salad as long as all 3 items are in there. This one's a permutation. It's stuck. This one's a permutation because order is going to result. Depending on what order I have the 472 is either going to open that locker or it is not going to open that locker. So in fact, you shouldn't be calling your locks combination locks. They're actually permutation locks. Permutation is where order matters. Combination is where order does not matter. So we used the example yesterday if I'm selecting 4 officers. And I specifically said we have a president, a secretary, what else we got? A vice president, and treasurer. Okay, thank you. So those are 4 specific spots. You care which one you get. On the flip side, so that would be a permutation. On the flip side, a combination that would look just like that if I was hiring 4 officers. Officer 1, Officer 2, Officer 3, and Officer 4, that they all carry the same level of ability. You don't care which one you get. That would be a combination. Because whether you're Officer 1, 2, or 3, or 4 doesn't matter. So order doesn't matter as long as you're one of those 4. That would be a combination. Let's put our combinations and permutations side by side. So the first one is permutation. Order matters. Order matters. Depending on what's picked first, second, or third, it changes the outcome. So for permutation, order matters. For permutation, we use the symbol P, and then we use N, comma, R. We also sometimes use this one where we have N, P, and R. Both those things mean the same thing. Our formula for a permutation is going to be N factorial all over N minus R factorial. For combination, order does not matter. Order will not change the outcome of the specific problem. So in this one, it does not matter. There's kind of 3 ways to do this one. You have ones that look just like the permutation where you have C, N, comma R. We also have one that's N, C, R. But more often than not, when we're using equations, we're actually going to use a parenthesis where we just have N over R. There's actually no combination C in it at all. It is just parenthesis N over R. That automatically means combination. So you can use any one of those 3 and it automatically means combination. You're going to see the formula for combination looks a lot like permutations where you have the N factorial on top. You have a bigger number on top. And once again, you're going to do N minus R factorial. But there's a small addition to it. Combinations are going to have a lot less possibilities. Because order doesn't matter if I have grapes something something. No matter what order they're in, they all count as just 1. Where a permutation, every order needs to be counted. So we're going to have less numbers in our combinations. So in fact, we're going to divide this by R factorial. So we're going to have N minus R factorial times R factorial. That's only because you're eliminating all the ones that were order mattered. All right, so that's permutation, that is combination. They seem easy on the surface, order matters, order doesn't matter, but it gets more complicated. You really have to think through a lot of these problems. So we're just going to do some together. So we have example 1. We're supposed to solve either using permutation or combination formula. Before I decide what one we're going to use, you first have to determine does order matter? Does that affect the outcome? Or does it not matter? So we have a 3-person committee is needed to study ways of improving public transportation. How many committees could be formed from 8 people on the board of supervisors? So it's just a committee of 3 people. They all have equal powers. Does order matter? Do you care if you're committee member number 1, 2, or 3? Yeah, read it. No, order does not matter. It's just 3 equal people. You're just pulling 3 people. Think about that. I'm just selecting 3 people. I don't care what order they're in. I'm just grabbing 3 people and putting them over here and say, hey, you're on this committee. I'm not organizing them as president, vice president. There's no organization. It's just I grab 3 people, put them off to the side. So order does not matter. No, it doesn't. So as soon as you go order doesn't matter, then you're going to use combination. All right, with combination, it works just like permutation. When I'm writing it down, we're going to say, how many total people do I have? I have 8 people to start off with. So I'm going to have C which is 8, and then we're going to choose 3. 8 people, choose 3 of them. So with permutation, I used pick. I would say 8, pick 3. For combination, I say 8, choose 3. All right, so now plugging this into our formula. Same kind of principle. We take the bigger of the two numbers. That would be our 8 factorial. It'll be all over 8 minus 3 factorial times 3 factorial. Simplifying this, we could have 8 factorial over 5 factorial times 3 factorial. Let's do this one by hand, or as much as we can by hand, because as I said on the test, there could be problems where I could say you can't use a calculator at all. They have to do this entirely in your head or on paper. So let's see how far we can go with this one. All right, so we have 8 factorial, which would be 8 times 7 times 6 times 5 factorial. Are we okay? Do you remember that we can stop here? Ask if this doesn't make sense, because this is what this is all based on. All right, then that would be all over 5 factorial times 3 factorial. Well, our 5 factorials would cancel out. In fact, I'm going to go one step further. I'm going to look at that 3 factorial. I'm going to rewrite it as 3 times 2 times 1. Because we can go further now. What's 3 times 2? 6, right? Seems too simple to ask. That 6 is going to cancel out with that 6 right there. Yeah.
And you don't if you mess up on that and don't realize that 6 and 3 times 2 would cancel out, it's not going to affect your answer.
No, it's not going to affect your answer at all. It's just, if you cross out enough stuff, I just have to multiply 8 times 7. Where you just would have had to do 8 times 7 times 6 and divide that out. Just know you can keep going, crossing things out. You could cross this 2 out with the 6 and turn it into a 3. Or you could do this 2, 8 and change that to a 4. It's just you're pre-dividing stuff. You're making it as simplified as possible. All right, so we have 8 times 7, which is just 56 possible ways. All right, so this would definitely be a problem. I could say you can't use your calculators at all on. That you have to do it all by hand. But if you don't know how to do this, then by hand you're doing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 on a timed test. I wouldn't want to have to do that. All right, our next one. We have 12 students help with a project. The director needs 3 telephone solicitors, 4 door-to-door solicitors, and 5 magicians. In how many ways can these jobs be assigned? So this is kind of a step up. So let's look at this individually. I'm choosing 3 people to be telephone solicitors. Is there a difference if you're solicitor 1, 2, or 3? Is there any difference? Do you care? No. So order's not going to matter. Is order going to matter if you're one of these door solicitors? No. And does it matter if you're one of the 5 magicians? No. Order's not going to matter. You're just grabbing 3 people and you're shoving them somewhere. You're grabbing like 4 people, shoving them there. You're grabbing 5 people and you're shoving them over there. You don't care. You're not organizing them. You're just grabbing them and pushing them in this direction. So order does not matter. Nope. So that means we need to use combination. All right, and this is going to be kind of a series of combinations. Let's do the first thing. So we start with 12 students. All right, we have 12 students, so we're going to have 12. And the first thing we're going to do is we're going to choose 3 telephone solicitors. So that's going to be 12, choose 3. All right, now with the remaining ones, I need to pick 4 of the remaining ones to be door solicitors. Do I have 12 people to choose from? No. I lost 3 because I'm going to choose them here. So this is for my telephone. Then let's talk about our door-to-door. That's going to be not 12 anymore, but we're going to have 9 people left. We'll have 9 choose. What are we doing? 4. All right, so that's going to be our door. And then finally, we are going to have our magicians, which is going to be, we have 5 people, and we are picking 5 of them. All right, I should have slid this over a little bit further. All right. Now, this is still going to be our fundamental counting theorem. Rather than choosing one from each group, we're choosing a few from each group. So we are still going to multiply these out. It's still a branching kind of thing. Depending on what 3 I pick, it will branch into what 4 I pick, into what 5 I pick. So this is going to turn into a multiplication problem, which is going to look like this, where we have 12 factorial over 12 minus 3 factorial, which would be 9 factorial, times 3 factorial. Then we are multiplying by 9 factorial, all over 9 minus 4, which would be 5 factorial, times 4 factorial. If you need to put the notes in there, you can. So that 9 came from 12 minus 3. This 5 came from 9 minus 4. And then we're going to have times 5 factorial over 5 minus 5 is 1 factorial times 5 factorial. This one is 5 minus 5. Let's stop at that 5, choose 5. If I have 5 people, how many ways are there for me to grab 5 people? Yeah.
Just one.
Just one way. Does the math support that?
Yeah.
5 factorial divided by 5 factorial. There's only one way to grab them. Yeah, read.
Isn't that one supposed to be a 0?
Which one's supposed to be a 0?
On
Oh, I'm sorry, yes. Yeah, they're both equal to each other. That's why I didn't quite. I meant to say 1, and then I added the factorial, but it's 0 factorial, which actually equals 1. Don't forget that 0 factorial equals 1. So that is 5 factorial divided by 5 factorial. In these cases, in a problem like this, I might let you use your calculator on this one, because it's just a lot easier. So it might be a good idea to take out your calculator and find your factorial button. Your factorial button will be hidden in your math button section. So if you hit your math button and scroll to your right, you'll see a probability section, and then you can use your factorial button. So why don't you take a second to try to do this whole problem. And then we'll talk about how you could do a problem like this kind of by hand. You could simplify it. Raise your hand if you're stuck and you can't find what I'm talking about. There's a 9 factorial. Well, there's a 9 factorial up here. So you could eliminate your 9 factorial and your 9 factorial. That's going to reduce this down to just 12 factorial over 5 factorial times 4 factorial times 3 factorial. It'd make it a lot easier to plug in your calculator because you don't have to worry about parentheses as much, but you still have to put your bottom ones in parentheses. So put your 5 factorial times 4 factorial times 3 factorial in parentheses. So if you're plugging this in your calculator, make sure that you have parentheses around your denominator. Like I said, if anything, overuse parentheses in your calculator. Always put everything in your numerator in parentheses and put everything in your denominator in parentheses. You're more likely to get things correct. You could also simplify this further. You could rewrite 12 factorial as 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 factorial. Cross out your 5 factorials. You could cross out other stuff. So this is one that you could potentially do a lot by hand. But more than likely, we're going to plug at least some of this in our calculator, and we should come out with 27,720 different ways. All right, so this is a combination problem that's combined with a fundamental counting theorem problem, where you're pulling something from one group, pulling something from another group, and pulling something from another group. This time, however, I'm pulling 3, I'm pulling 4, I'm pulling 5. This will also work with a permutation. So if we had multiple, like we have 3 people being telephone solicitors, but one's a head solicitor and one's below it and one's slightly below it, then it could be a permutation. All right, let's go on to this next one. We have 50 people purchasing raffle tickets. 3 winning tickets are selected at random. If first prize is $500, second prize is $100, and third is $50, how many different ways can the prizes be awarded? Does order matter? Brian? Yes, it does. I'm no longer just grabbing 3 people. I'm grabbing 3 people and saying, hey, you're first, you're second, and you're third. So I'm dividing them up after I pick them. For the telephone solicitors, I'm just grabbing them and throwing them saying you're all on the telephone. So order does matter. So this is going to be a permutation. All right, so we have 50 people purchasing raffle tickets. So we said it's a permutation. We are going to have 50 people, and we're going to pick 3 of them to win. So it's 50 pick 3. Well, in this case, we're going to have 50 factorial all over 50 minus 3 factorial. In other words, we're going to have 50 factorial over 47 factorial. Once again, I don't need a factorial button to solve this one. We can rewrite 50 factorial as 50 times 49 times 48 times 47 factorial. That would be all over 47 factorial. Our 47 factorials will cancel out. So even if you have a scientific calculator, you can just type in 50 times 49 times 48, and you should have your answer. And I got out 117,600. All right, so a big thing on the homework is going to be deciding if order matters or it doesn't matter. A good thing to ask, are you just grabbing things and throwing them off to the side and putting them in one group? Or are you grabbing things and then assigning them specific spots? Like when we did our batting order, we grabbed 9 people, but then we said you're first, you're second, you're third, you're fourth. So ask, once you decide your group, are you subdividing them into smaller sections? That's going to be whether order matters or not. All right, next thing we're going to talk about are identical objects. These are going to be ones where order matters and doesn't matter at the same time. And what I mean by that is, let's say you have to spell the word Mississippi, and you want to know how many different ways there are to rearrange those letters to make new words. Not really words, but how many ways are there to rearrange it and have something new? Well, the thing is with Mississippi, there is no first S, second S, third S, and fourth S. So if I look at Mississippi and I flip these 2 S's, I didn't change the word. If I take these 2 I's and flip them, I didn't change the word, so I don't want to count those. The only thing I want to count is if I switch like an I and an M. If I switch an S and an I. Those are the only ones I want to count. So we have a whole bunch of things that we need to eliminate. We need to eliminate any words that are the exact same. So whenever we're doing something such as this, where there's identical objects that can appear, what we're going to do is, if we have subsets of identical objects, R1, R2, R6, where R1 plus R2 plus equals N, is N factorial over our different things. Now, it looks really complicated, but let's just deal with it with just the word Mississippi. We'll do it together, and it's going to make a lot more sense. All right, the first thing you're going to do is count how many elements you have. So in Mississippi, there are 11 letters. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, we have 11 letters. All right, now you're going to look for the different elements or different letters you have. You're going to ask yourself, how many M's are there? There's one M. Go to your next letter. How many I's are there? There are 1, 2, 3, 4 I's. How many S's are there? We have 1, 2, 3, 4 S's. And how many P's are there? There are 2 P's. That is 8 plus 2 plus 1 equals 11. These are your R values. These are, in fact, your R values. So to come up with how many different ways there are to arrange this, we're going to start with 11 factorial. 11 factorial is actually how many different ways there are to arrange Mississippi without counting any repeats. This comes from the fact that it is our first letter. We have 11 to choose from. Then we have 10 to choose from. Then we have 9. Then we have 8, all the way down. So it's 11 factorial. This is how many different ways there are to rewrite Mississippi. But now I want to get rid of how many repeats. I want to get rid of, at any time, 2 S's just swap places, or any time 2 I's swap places. All we're going to do is we're going to divide everything by our repeat letters. So that's 1 factorial times 4 factorial times 4 factorial times 2 factorial. And that's just going to come out to being 34,650. Once again, 11 factorial is how many different ways I can rewrite Mississippi using those letters, or how many different words you can come up with those letters. And these get rid of any repeat Mississippis where the S's just switched, or where the I's just switched. Now, I know this is buried on this side of the sheet, but it's important. You need to know it for the test. You do need to know this for the test. Don't forget about it. All right, the very last example we're going to do is one where we have a company employing 9 male welders, 7 female welders, and then it says how many different committees can be formed of 3 male welders and 2 female welders have to be in that committee. All right, so we're forming a committee. There has to be 3 male and 2 female on it. So that means we're setting up 2 different situations. I am choosing 3 men from a group, and I'm choosing 2 women from a group, and putting them together on this committee. Now, when I grab the 3 guys or 2 girls, am I assigning them specific roles on the committee? Does this say anything about specific roles? So does order matter? Or am I just grabbing 3 people and saying you're on the committee? I'm just grabbing 3 people and saying you're on the committee, so order doesn't matter after that, so we're definitely using combination. Order does not matter, so we are using combination. Let's talk about the male employees first. The male employees. We're doing a combination. We start with 9 males, and we're selecting 3 of them and throwing them on a committee. Order doesn't matter, so we're going to have a combination, and we're going to say, okay, we start with 9, and we're going to choose 3. The female employees have the exact same thing, except we only have 7 females. So we have 7 females, and we're going to select 2 of those to be on that same committee. Once again, this is the fundamental counting principle. We are choosing 3 here and 2 here, so to come up with the total, we're just going to multiply those 2 together. So we're going to have 9 choose 3 times 7 choose 2. That's going to equal 9 factorial over 9 minus 3. I guess we can actually do this in 9 minus 3. We should have room times 3 factorial. And we're going to multiply that by 7 factorial over 7 minus 2 factorial times 2 factorial. Let's simplify this down. We'd have 9 factorial over 6 factorial times 3 factorial. That would be times 7 factorial over 5 factorial times 2 factorial. That's a lot of factorials going on. Well, we can simplify this. We can simplify this further. Now, 9 factorial becomes 9 times 8 times 7 times 6 factorial. So in fact, I really just have 9 times 8 times 7 over 3 times 2 for this one. For the other one, I have 7 times 6 times 5 factorial. So really, we just have 7 times 6 over 2 times 1. I guess I should have the times 1 there. Well, we can go further. We can say 3 times 2 is 6. That will cancel out that 6. We have 2 and an 8. So let's go ahead and I'll circle that 2. And that 8 divided by 2 is actually just 4. So at the end of the day, I just have 9 times 4 times 7 times 7. That is all stuff you could do on any calculator. So that's going to equal 1764. Know how to reduce factorials by hand. Once again, you will not be surprised on the test when I say you cannot use your calculator at all. Or you can use a scientific calculator in this section. And I do have scientific calculators. You have to know how to reduce these. Otherwise, like I said, you're going to be on a timed test doing 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 in a calculator. And then trying to divide it by, 8 times 2 times 7 times 6 times 5. Know how to reduce these. All right, any questions for me on this? Brody, any questions? No, you're good? Yeah. All right. All right, guys. Have a good weekend. Make sure you get this done.